Okay. Welcome to the second session today, and I want to tell everybody that you will be able to recover the recordings in a day of every session, and the link is inside the document of the WordPress. Ronnie Katzir is an associate professor in the Department of Linguistics and a member of the Sagol School of Neuroscience at Tel Aviv University. His work uses mathematical and computational tools to study questions about linguistic cognition, such as how humans represent and learn their knowledge of language and how they use this knowledge to make inferences and contribute to the discourse. Ronnie received his BSc in mathematics from Tel Aviv University, his PhD in linguistics from MIT. He heads Tel Aviv University's computational linguistics lab and its undergraduate program in computational linguistics, and is a tutor in the Adi Lautman interdisciplinary program for outstanding students. You'll have to send us your outstanding students. Welcome, and you're on.
Thank you, Stephen. Let me just share my slides. I'll be talking about if and how we want to go from the excitement about the remarkable engineering progress in the domain of neural networks to any claims about cognitive science, in particular human linguistic cognition. And of course, the excitement about the engineering successes of the past decade and more, that excitement is very understandable. We asked ChatGPT to write a Shakespearean sonnet about itself and human linguistic cognition, and it writes something. I mean, it's not great poetry, but it's still impressive, and it's something that would have looked like science fiction just a decade ago. But this is engineering, and the question is whether we want to draw any conclusions from this engineering progress when we conclusions to the study of mind, of the human mind. And here there have been mixed reactions. So some people have said that these models are not really thinking models at all, that they're possibly irrelevant to the study of mind. A very catchy term that was used by Emily Bender and colleagues is that these models are just stochastic parrots. They memorize stuff and then they throw it back at us in some probabilistic way. And that's one view. But of course, lots of other people have reached different conclusions. We heard here on the first day in Richard Futrell's talk, the idea that perhaps these models already capture somehow the grammatical structure of language. There have been claims that the activity of the networks somehow corresponds very closely to our brain activities. There is a recent paper, I think we'll hear more about that in Kyle's talk tomorrow, about how LLMs have reached some kind of formal competence, formal linguistic competence. And there was Steve Piantodosi's paper last year that claimed that LLMs basically replace all of theoretical linguistics, that they are the way to do linguistics these days. Okay. Just for convenience, I'll use the term the LLM theory for the idea that that key aspects of our human linguistic cognition are shared with LLMs. And of course, there can be lots of different variants of this broad umbrella term. Maybe we share the representations, maybe the learning processes, maybe some other things. I just will use this term occasionally to make it easier to refer to this family of views without implying that they're all the same somehow. Now, to begin with, there is something that is surprising about the claim that LLMs teach us about human linguistic cognition. In other domains, and to use maybe the most familiar example in these discussions, in other domains, we usually draw a clear distinction between empirical science and engineering. So if we want to study flying, we might be interested in things that fly in the world, like this albatross over here on the top left, or we might want to be in the business of constructing flying things, and that's engineering, like Otto Lilienthal on the bottom left and the Wright brothers, Kitty Hawk on the bottom right. Those are two very different enterprises, even if some people would be interested in both, and sometimes tools from one domain can be useful in another. Those are very different projects. When it comes to thinking, to cognition, things, for some reason, tend to get blurred, but the distinction is the same. We might be interested in things that think in the world and study perhaps ourselves, perhaps other organisms, or we might be in the business of constructing thinking things or talking things and build all kinds of machines that do that. It's not at all clear that there will be a lot of overlap between the domains, even though, again, the same person might be interested in both, and occasionally a discovery in one domain might be helpful in another, but a priori, we can't assume that. So how do we study linguistic cognition? And here I'm just repeating something that I had on a slide a couple of days ago after Richard's talk. And so we perform inference to the best explanation in all empirical domains. This is not specific to cognition in any way. So we try to explain, we look at the data. Of course, we care a lot about the data, but we try to find the best theory, okay, the best explanation. We don't try to match surface frequencies. We don't get too worried when there are exceptions. That's not the thing that we should care about when we construct our theories. We try to build good theories and we compare them. And then we can talk about laws, and laws are just big identifiable parts of best explanations. And laws might be not at all surface true. They might have many exceptions because laws might apply, and then other things might happen along the way that will obscure the observation. So we might have a really good theory of how objects fall, but then there are things like wind and friction and so on that make our observations much messier than we would expect just by looking at the law itself. But this is what we do generally when we try to study an empirical domain, and the same holds in the domain of cognition. And so one would expect that if LLMs are proposed as a serious theory, then this should be done in these terms as an attempt to say, look, we have a better explanation. We know, and we engage with the existing explanations from, in the case of linguistics, at least 70 years of serious theorizing on the topic. And in some cases, some additional centuries and millennia of discoveries in this domain. And we take this into account, and we're showing you that LLMs provide a better theory. That should be the standard by which we evaluate the LLM theory. We compare it to existing explanations, in light of existing discoveries. And explanations in this domain, and this includes LLMs, all share several ingredients that interact in all kinds of interesting ways. We can talk about the representation. So we're born with something, and we can disagree on what it is that we're born with, and there have been lots of different ideas and proposals and arguments for what we're born with, but we are born with something. That's something that everyone agrees with. This is, so you can think of it, since we're used to talking about linguistic knowledge as computational, at least in part, since the 1950s. We can talk about this innate part as the innate programming language, the thing that we're born with. Now, this can be a way of writing context-free grammars, or it can be Python, or it can be all kinds of things. It can also be LLMs. LLMs provide their own programming language. Each proposal is a way in which we can then write different weights, just numbers in the connections between the units. And so that's the representational part. So everyone has that component. In linguistics, this got the name universal grammar, which can be a confusing term. So I'll try not to use it a lot. I think it's enough if we talk about the innate programming language. That's one factor. Another factor in explaining things is learning. And we just heard Charles talking about that in the previous talk. I'll talk more about this soon. And of course, this is a major issue in all the discussions of the current models. And we heard different ideas about this the past couple of days. We'll hear more, I'm sure, of the coming days as well. Communication presumably plays an important role in shaping the languages that we see around. So part of the data that we need to account for needs to be understood in terms of communication. So that's another factor. Processing, resources, and many other things. This is by no means an attempt to provide an exhaustive list, but these are all parts of an explanation, and all evaluations of LLMs or anything else in the domain of cognition should tell us what the proposal is really, what the explanation is, and why it is better than other explanations. Something that is usually assumed but not in the LLM world is the following, which is sometimes attributed to Galileo, and that is that if we want to discover things about the world, it's a very good idea to start from the assumption that we can understand it, that the world can be understood, and then if there are things to understand, we have we might be able to discover them by trying all kinds of things, failing, correcting ourselves, improving our explanations. If we start from the assumption that nothing can be understood, then even if there are things that can be understood, we'll miss them. And in a sense, the LLM theory starts from that position, from saying everything is so complex. Let's take something with hundreds of billions of parameters that is completely opaque and that we have a really hard time looking into. And that will be our starting assumption. And that makes it extremely difficult to discover things. Even if there are very simple things that can be discovered, this starting point will make that really hard. And that's something I think to keep in mind. So these are some general a priori considerations. And I think the fact that we're taking an engineering tool and a very opaque one and using that as a starting point, if we're following the LLM theory, that's going to make it really hard for us to see what's happening. It makes it, I think, quite unlikely a priori that we'll find things. Both because what are the chances that this engineering tool will just happen to be like us? And because if we start from something so opaque, it'll be extremely difficult for us to see what actually happens. For now, let's put these general considerations aside and look at some of the empirical data. And there are multiple places where we can see that the LLM theory either hasn't told us yet how it will deal with well-known challenges in the study of cognition, or it makes very clear predictions that seem to be completely wrong. And really, I'm going to follow here proposals and observations and forms of argument that were formulated over half a century ago and that have been very central to linguistics and parts of several other domains since then, and places where we could have said in advance, we could have pointed out in advance that LLMs were going to have a problem. So I'll start with something that is maybe not the most not the most exciting empirical question in the area of LLMs, but it will be helpful for us to have that in the background, and that is competence versus performance. And we know this distinction not just from the study of language, from lots and lots of different places. When children try to walk, they very often try to succeed. They try to get somewhere and get there perhaps in a straight line, but they very often fail. They're not well enough coordinated to do that. It happens to adults too, just maybe a bit less frequently, so we notice it less. But we very often at different ages try to walk a certain way. That's our competence telling us how we're what we're trying to do, and our performance just gets in the way, and all kinds of muscle and coordination problems make us fall and yesterday Virginia was showing us a developmental area where it looks like there is a very striking kind of division between competence and performance with respect to utterances produced by children. One of the classic examples of the competence performance distinction is what happens with center embedding, where we know what happens. So here is a sentence. I just gave this to ChatGPT with GPT, in this case, with GPT-3 a year ago. The mouse and the cat that the dog painted thought sang, and ChatGPT at that time got completely confused by that sentence. But the more relevant point here is, since then in GPT-4, this has been fixed, but there are other cases that we could look at. They're just longer. The main point here is that humans follow a very clear pattern with these sentences. We find it hard. We find such sentences hard. We make mistakes and so on. But if we look at them longer, if we sit in a quiet room, if we sleep better at night and so on, then we'll perform better. And if there's noise, if we have a parallel task and so on, then we'll perform worse. We know what the correct thing to do is. It's just that we struggle in harnessing our resources in real time to deal with this. This is not something that LLMs have, to the best of our knowledge. I mean, it hasn't, if they have a distinction of this kind, then it hasn't been pointed out. There are ways to simulate that, and LLMs in different ways can be made to behave as if they have this distinction. But when you look at the architecture, there is no sense in which center embedding is harder, more difficult in terms of the resources that are used, that memory is somehow needed here in a way that it isn't in cases that don't involve center embedding. Okay, and that's something to keep in mind. And now for something that I think is more interesting inherently, and also more worrying for the role of LLMs in society. And that is the distinction between what is correct and what is probable. And we have this distinction in lots of different domains. We know that certain things are the right thing, but a very unlikely thing. So in scientific discoveries, so the discovery itself might be something that is completely surprising, but the discovery was made, and if there are good arguments, then it is correct, even though it's unlikely. So Richard brought up Kepler's discoveries, but when Kepler formulated his laws of planetary motion, those laws were very surprising. The elliptical orbits, no LLM at the time would have predicted that kind of sentence, but it turned out to be correct. And we have it in lots of areas. In art, so good artistic creations are things that are surprising. No one would have predicted them at the time, but they are correct according to something, and we know that they're correct. Not everything that is surprising works. Some things do. Beethoven's late string quartets work, even though they were shocking at the time. Cubism works, even though it was strange and shocking at the time too. And we find that in lots of different domains, and including in language. In language, we have many cases where something is just correct but unlikely. Here is something that I checked with GPT-4 also about a year ago. A continuation of a sentence, the little duck that met the horses with the blue spots yesterday, and two possible continuations. One is R, which is likely, but it's a common error. There is an agreement problem here. It doesn't match the subject. Or destroys, which is grammatical, it is correct, but unlikely. And GPT-4, at least at the time, got the wrong result here. It went for what's probable. Richard was talking about something similar a couple of days ago and had a very nice example with two sentences, or one grammatical but unlikely sentence, and some incorrect word salad that the LLMs preferred, and there are lots of these. We have this distinction. We can look at those cases in all these different domains, and we know that some things are right but unlikely, and that other things are likely but incorrect. And LLMs don't, and they architecturally don't have that. When you look at the architecture at the network itself, it only outputs probability. That's the only thing it knows how to output. Okay, so for when we try to squeeze something like correctness out of networks, it's a trick. It's trying to make it predict something probabilistically that we will treat as a correctness judgment, but that's not what the network says. For the network, there is no notion of truth. It's not even getting correctness wrong. It doesn't have that category. And I think that's worrying for the role of these models in all kinds of places that affect society, because something that doesn't have a notion of truth is scary, and something that doesn't have a notion of correctness or truth and knows how to hide it so well is even scarier. But here, for the study of cognition, it's just clear that something essential is missing, a clear category is missing. Then there are all these many different ways in which our representations, so the things that come from the programming language and the learning that we have are completely different from what we see with networks. And Richard mentioned on Monday the argument from the poverty of the stimulus, and then it came up again yesterday a couple of times. And here I'm just going to assume the following form of of argumentation that goes under this name, and that has been quite central to discussions, and this is the following. So if humans systematically arrive at a certain piece of knowledge given certain data, and if we can show that linguistically neutral learners don't do that, then humans are not linguistically neutral. If we just show that linguistically neutrals fail to reach that knowledge and that humans do. And so humans come to the task somehow prepared or biased in this direction. And Richard suggested that LLMs show that it's easy to learn, and that an argument from the poverty of the stimulus falls apart. And I'm going to try to show that that's not the case, or mention a few observations that suggest that this is simply not the case, and that LLMs are, first of all, that they're very different from us in terms of representations and learning, and second, that that the argument from the poverty of the stimulus might be even strengthened when we use LLMs to evaluate how much information there is in a corpus, but that's more tentative. Ideally, so LLMs are not great for conducting this discussion of the poverty of the stimulus. So that's why I mentioned that the more constructive conclusion will be tentative. So ideally, what we would do is we would take a very powerful learner that is clearly capable of learning the kind of knowledge that we're interested in, but is also clearly not biased in any way, in any way that favors linguistic knowledge. All learners are biased in one way or another. We would train this learner on a corpus that is something like what children see, and then we would inspect the learner and see what it learned. Now, with LLMs, we can't do any of these three things. So they're not sufficiently powerful. I'll say more about this in a moment. They're not sufficiently powerful to learn basic things that humans know. We don't know enough about their biases to just claim that they're not linguistically biased. We don't know how the many decades of working on them, in what ways these decades made them biased in ways that we don't know, and that are hard to read. At this point, we don't have good enough corpora that correspond to everything that a child is exposed to over the first few years of their life. That also is something that came up during the talks and conversations here. And finally, we can take LLMs and look at their knowledge. First of all, they don't tell us things directly about grammaticality or knowledge. As I mentioned, they don't have that distinction, but even if we use them as some kind of proxy for a future learner that can talk about correctness, we just don't know. We can't read what's there. Still, we might be able to use them in certain ways, and at least as proxies, as something that would give us suggestive arguments. And there have been several such papers recently. The paper by Wilcox, Futrell, and Levy that Richard was mentioning uses LLMs in this way to say that there is no argument from the poverty of the stimulus in the case of WH movement. I'll have some examples in a moment for those of you who are not familiar with that. For the things that we find in questions and in all kinds of other long distance dependencies in syntax. And they suggest that these LLMs are able to reach the knowledge that humans have, and that this dismantles the claims in the linguistic literature that we are special in that we're prepared somehow to acquire this knowledge. So LLMs are supposed to show that anything could learn it. Now, so this is, I want to make the following small point, that we're not talking here about whether it's easy or hard to learn syntax. So Richard was saying that acquiring syntaxes turns out not to be that difficult. I don't know what exactly he meant by that, we didn't have time to get into that in the conversation. There are different ways to understand difficult, but the argument from the poverty of the stimulus is not that it's hard to learn in general, or it's hard to learn syntax or anything of that kind. And it's really about being able to reach certain conclusions based on a certain amount of input, and if a good general learner can make that kind of inference from the data, then we don't have an argument. If such general purpose learners fail and humans succeed, then then we have an argument of this kind. Okay, I'm just basically repeating what I had on the previous slide, and it's this is what we're talking about here, not about. So linguists are not claiming. I don't think linguists often claim that it's just hard to learn or things like that. It's about very specific inductive leaps based on very specific corpora, and the claim here is that in the literature, in the linguistic literature, the idea is that that there is not enough information in the corpus that children see that will allow them to acquire the specific kinds of knowledge of WH movement that they do. And the claim by Wilcox and colleagues is that that's not the case, and that LLMs succeed in acquiring this knowledge from comparable corpora, and that therefore the linguistic claims are wrong. And now I'm going to talk about recent work that Nurlan, Emmanuel Shemla, and I did, that just probes this question a bit further. And we, as far as we can tell, the claims about LLMs are very much premature. That in fact, LLMs provide no evidence that a general purpose learner would succeed in acquiring these dependencies, these WH movement dependencies, filler gap dependencies. So we looked at a bunch of different models listed here, and trained on corpora ranging from about 10 months of linguistic experience to over 10,000 years of linguistic experience. And we followed Wilcox, Futrell, and Levy in the general kind of paradigms that we were looking at, and they looked at things like this. So who, the dependency between who, the filler, and the gap here, the empty space here between with and yesterday in 1A. I know who you talked with, gap, yesterday, that's good. But I know who you talked with, Mary, no gap, still a filler, but no gap, yesterday, that's not good. And if we don't have the filler, if we don't have who, we have that instead, then we cannot have a gap here. I know that you talked with gap yesterday, no good. I know that you talked with Mary yesterday, no filler, no gap, that is good. And as Wilcox and colleagues discovered, LLMs can make the correct guess here in simple cases. What's the correct guess? They don't, these models, as I mentioned, don't give us grammaticality judgments. What they can say is just probability. And probabilistically, we would expect any model that was able to figure out the pattern roughly to give a much higher probability, much higher to the grammatical continuation, because it's also the likelier one. This is a case where grammatical and probable happen to be well aligned. So we'd expect a much higher probability to the correct continuation. But so what we did in our paper is we looked at some more cases of this kind and pushed it just a little bit beyond those very simple cases. So here is one out of two main cases that we looked at, and that is what happens when you have coordination A and B. And in these cases, if you have a gap in one conjunct, then you must have a gap in the other conjunct. So if you have a gap just in one, that's generally not okay. There are some well-studied exceptions, but in general, that's not okay. So 2A is not good. What fruit did John buy an orange? No gap. And Mary sell? Gap, that's not good. What fruit did John buy and Mary sell? That is good. Similarly, in 3, I know who John praised gap yesterday and will insult you, no gap tomorrow. Not good. I know who John praised yesterday and will insult tomorrow, gap in both conjuncts. That is good. Here, all the models assign, it's not just that they fail to assign a much higher probability to the correct continuation, they actually prefer the incorrect continuation. Okay? All of them, trained on different corpora of different sizes, they all fail, including those that were trained on 10,000, 30,000 years of linguistic input. That was just graphs with one sentence, but we looked at thousands of different lexical configurations, and with the exception of GPT-3, all the models, including the very large ones, guessed preferred the incorrect continuation in most of the cases. Okay, so we can already conclude that the networks are not showing us that they learned the pattern. In fact, very soon I'll show you that there are reasons to think that the networks cannot really learn the pattern, but they don't even approximate it. Okay, they're not even close. They're failing completely. Almost all the time, they're actually preferring the incorrect continuation. So they're certainly not showing us that the argument from the positive, the stimulus, doesn't go through. Okay, for that we would need a general unbiased learner that is successful after about 8 years, which is here around the Wikipedia models, or maybe earlier. So between Childless and Wikipedia, GPT-2 is already hundreds of years of linguistic exposure, and GPT-J and 3 is thousands of years. So even with hundreds and more of years of linguistic experience, current models, maybe future models will succeed here, but current models simply don't show us that there is a problem with the argument from the paucity of the stimulus. Much more tentatively, we retrained one of the models, the Wikipedia transformer, with additional examples, just a couple of hundred of examples of the relevant kinds of constructions, and the performance improved a lot, which suggests that the models in principle, even though, again, they're not going to be able to learn the pattern exactly, they are able to approximate it way better than what they did when trained on the original corpora, which suggests that the original corpora are just not rich enough to support this kind of inference. Another thing that is highly informative about what we're born with is the typology. So we look at different languages and we analyze in depth different languages, and then we try to reason about what we need to be. Okay, what's a good theory of us? Again, we're doing inference to the best explanation. What's the best explanation that would explain why all languages have this or that property, or why most languages are like this? And again, here are the factors that I had earlier, the representations, UG, yeah, okay, the innate programming language, learning, communication, processing, and so on. There can be all kinds of other things that are part of the explanation, but we need to reason about these. We need to say, okay, in light of what we're seeing, of the data we're seeing, we conclude that perhaps the programming language has this property or that property, or that the learning mechanism is like this or like that, or that communication works in a certain way, and so on. And here are some very central and, in a sense, straightforward aspects of competence, straightforward to describe. I mean, the discoveries themselves were very significant and remarkable, but it's easy to understand what we're talking about here in these things. And then I'll have things that are a bit trickier to describe. So the fact that natural language seems to rely very heavily on bracketing. This is something that came up a couple of days ago. So John will talk to Kim. So to Kim is bracketed together, talk to Kim is bracketed together. And then if we place things in an unexpected place in the beginning of the sentence, talk to Kim, John will, that's okay. But we can only place things that are bracketed together here in this position. So we can say Kim John will talk to, or to Kim, John will talk, or talk to Kim, John will. All of these are okay. But when we take something that is not bracketed together, talk to, John will Kim, that's bad. Okay. And this is something that is not just about English. It's something that we see in many, many, many different languages. In fact, it's hard to make the case that that languages can choose to ignore this, even though some languages have very free word order. There is still some evidence for constituency there. And this is something we need to explain. It's something we need to derive. In linguistics, since the very beginning of generative linguistics, this has been part of the story. And it usually goes into the programming language here, the representations, the innate programming language. This is not something that LLMs derive. Okay? And to the best of my knowledge, there is not even an attempt to derive it. In fact, there is reason to think that LLMs can't even capture this, but they certainly don't derive it. In terms of the meanings that we have, entailment plays a very central role, which is part of a non-trivial explanation that I won't go through here, for why Kim spoke to every student who ever smoked is okay, but Kim spoke to some student who ever smoked is not okay. Okay, this is for many decades, the standard explanation has been in terms of entailment or subsethood in some sense. This is not something that, and again, it goes into the programming language when we talk about explanations in linguistics. LLMs don't capture this, and they certainly don't derive this. One other thing is that the meaning computations they make reference to structure, to syntax, but syntax doesn't make reference to meaning or to very small parts of very formal aspects of meaning. So there is modularity here. And there are other cases of modularity in the grammar. The arguments are non-trivial. I'll be happy to talk about them in the question period, but they're there. LLMs are inherently non-modular. It's not clear whether we can make them learn something that is so modular as what we have in our competence. LLMs certainly don't predict this. Many other cross-linguistic patterns, as I said, maybe a bit harder to describe, so I'll just mention them here and we can come back to them in the question period. One is what I already mentioned about if you have a gap in one conjunct, then you must have a gap in both. You see this in language after language. It's not just about English. Presumably, something about the programming language tells us to be like this, pushes us in this direction. It might have exceptions, but it pushes us in this direction. Not clear how LLMs could capture this, certainly not derive this. Other things like the fact that we can't ask a how question about a relative clause. So how do you know the mechanic who fixed the car? We can't answer with a hammer. For something very similar superficially, like how do you believe the mechanic fixed the car? We can certainly answer with a hammer, but not in relative clauses. And this seems to be without exception cross-linguistically. Certain lexicalizations never happen. We don't have a word that a quantifier like every or some or many or most or five that would be like this glebe here that is true exactly when there are more of the first argument than the second. So glebe boys smoke, exactly true when there are more boys than smokers. It's not a crazy meaning. We have the verb outnumber that means the same, but we just don't have quantifiers in any language that behave like this. Many other things, to my knowledge, not even the beginning of an explanation of this that doesn't make reference to the programming language or in any of the attempts to say that LLMs are plausible models of linguistic cognition. In the case of XOR, so the fact that we do not have a word for exclusive or for NAND in any language, we don't have a single morpheme for that. Richard mentioned a couple of works that that are in this neighborhood but don't provide explanations for this, and don't. So we mentioned the work that Emil Langar and Benjamin Spector did, and work by Shane Stein and Threlkeld, but those are not actual explanations, nor would the authors claim that they're explaining this here. And as far as I know, there really are no explanations at this point that don't make reference in one way or another to the programming language or something that LLMs could live with. And so these empirical failings that we just saw, I think, are major. These are all very big points about what makes our linguistic cognition what it is. And linguists have engaged with these challenges for many decades, and the LLM literature at this point seems either to remain completely silent on these, or to have real problems, like not having the right categories, not being able to even approximate the relevant parts here. In the remaining few minutes, I want to talk about something that looks like a particularly striking failure of LLMs, which would make them not just bad models of human linguistic cognition, but also bad models of any kind of thinking things. So bad scientists in general, something that would be bad in an alien or in anything really. So here is a very simple example. So a few strings here, all of them are A's followed by B's, followed by C's, followed by D's. And if you look a bit more closely, you'll see that the number of A's and the number of C's is always the same. The number of B's and the number of D's is always the same. We have no problem noticing that. We'd expect any scientist, of course, who looks at this, regardless of their to notice this. We'd expect children to notice this. Actually, we'd be disappointed if an alien who pretends to be intelligent would not notice this. This is a very basic generalization. Any thinking thing should be able to get this, but LLMs don't. This is what happened when I gave it to ChatGPT with GPT-4. I did it a year ago, then I repeated it recently, and the results are the same. It thinks that there could be E's in the end. It misses completely the fact that the A's and the C's should be balanced and the B's and the D's should be balanced. I tried to help it, nothing works. And so this is very embarrassing, I think, for any attempt to say that these models are automated scientists. If they can't get this right, then they're certainly not going to be automated scientists. They can help us, they can help scientists, they can be a fantastic tool to assist us, but they cannot reason, they cannot perform induction, they cannot notice basic patterns here. Now, in this particular case, I think there is a solution, and it's not my solution. It's in fact a very old solution. It was developed by Ray Solomonoff here on the left in the late 50s and published in 64, and also discovered independently by Kolmogorov and by Chaitin, and then made its way into a principle that is known as minimum description length, or MDL, which was brought up in the Q&A in the previous session after Charles's talk. And it's a very general principle of rational inference that says that when we try to be scientists, we try to find the best overall explanation. So we find the best in terms of the shortest computer program that prints out the data and then stops. Very often when we're talking about grammars, it's useful to distinguish between the grammar component here. I wrote it as G, and the data given the grammar, the encoding of the data given the grammar, D given G, and we try to minimize the sum total of these two quantities. And it corresponds very closely to things that people have talked about under the name of Bayesian inference, and it seems to match what subjects do in the lab on several different tasks. So in visual inferences of certain kinds and in fast mapping, it has been claimed that subjects follow this kind of optimization. In work in my lab from a few years ago, we used this principle to build all kinds of learners. Here in the bottom left here, a learner for phonology that just looks at surface data and acquires a full phonological grammar, including the lexicon of underlying representations, the phonological processes, the rules with their context and their ordering, which, to the best of my knowledge, remains the only learner in the literature that can do this kind of thing, that can start from just from the surface data and reach these kinds of grammars that are of the kind that some phonologists have proposed for our phonological knowledge. So this is the principle, and we can take this principle and use it with neural networks. Okay, and this is a paper that Nurlan, Khalgayer, Emmanuel, Shemla, and I have. It's from a couple of years ago, and we just used MDL, and we used that instead of the standard training that networks have been using, the same training for more or less for decades, that is based on essentially minimizing D given G, the likelihood, kind of maximizing the likelihood, minimizing D given G, cross entropy, the standard quantity that goes into backpropagation and that helps standard learners, networks learn. We replaced that with MDL, which was something that people looked at in the 1990s, but then more or less abandoned. And what we saw is that we get networks that succeed according to all kinds of metrics, they perform much better than all the standard networks that we looked at. And not only that, they reached perfect knowledge. So they given not so much data, they were able to, after learning converged, which we did with a genetic algorithm, they showed us their knowledge in the shape of a simple story. So the networks can actually be read, and you can prove that they'll be correct for all n, not just as an approximation, that they're really correct and they'll stay correct regardless of n. So this is for a to the n, b to the n, a to the n, b to the n, c to the n. You can follow the story here. They evolve counters. So the structure here, we didn't impose a structure. We let the learner search through this huge hypothesis space of different architectures, different connections, different weights, and so on. The broken lines here are recurrent edges. The solid lines are normal feed-forward edges. And in formal language after formal language, the learner arrived at a perfect network, a small transparent network where we could prove that it's correct for all n, not just as an approximation. This is for addition, which also standard learning doesn't work. Then we looked more closely at the objective function with different regularization options like L1 or L2. And what we saw is that we did it both with the simple architectures from the previous slides and with LSTMs. And we saw that standard objective functions, regardless of which choice of early stopping or actual regularization like L1 or L2, you use, your objective function will push you in the direction of a mistake. A point in the hypothesis space is simply incorrect. And MDL here on the right, so this is on the left, it's with L1, middle with L2, two kind of familiar regularization options. On the right, it's MDL, and it's only in MDL that the correct point in the space, the correct LSTM for a to the n, b to the n, and what the objective function chooses are aligned. In all the other cases, the correct thing and what the objective function wants are separate. So no matter how long you train these LSTMs and how much you try to make them better, they will not work with standard learning because the objective function is wrong. With MDL, you get the correct result. Okay, so just to briefly conclude, to evaluate the LLM theory, we need to talk about inference to the best explanation, simply because it's an empirical science that we're dealing with here, and that's how we make progress in empirical science. And the LLM theory fails. It fails to even approximate constituency. So something that can't learn at this point, a to the n, b to the n, is not going to get you constituency, let alone these more complex things that I showed earlier with WH movement. It's certainly not going to explain why language after language makes reference to constituency. Similarly, for modularity, for entailment, for competence versus performance, and so on. All these things that linguists have built into their explanations and have cared a lot about, and these things are not things that the LLM theory can even begin to explain, which means that it's just not on the right track. And given that we started from those a priori considerations, so what are the chances that an engineering breakthrough will somehow be a scientific theory, and what are the chances that we'll discover interesting things if we start from the assumption that the world cannot be understood. So given that starting point, the fact that the LLM theory fails so badly is not really surprising. Okay, so I know this sounded quite negative with respect to LLMs, but it isn't about LLMs being not good. They're fantastic engineering tools. It's about the LLM theory. Okay? LLMs are really remarkable engineering products. They do lots of things. They can help us in lots of things. Here, I use them to a bit earlier to illustrate a linguistic point, and there are of course tons of other ways in which they can be used, but they don't think. They don't work as scientists, not even as alien scientists. They fail at generalizing in the most basic way, and they're really, really, really bad as theories of human linguistic cognition. So if we go back to the question of whether these things are real theories of who we are or whether they're stochastic parrots, I think the answer is clear. And here, this is what they are. The only thing is that I feel a bit uncomfortable with this stochastic parrot thing, because I think biological parrots actually are intelligent. They're amazing creatures. They do think and they learn. LLMs don't. They're interesting in other ways, but they're not. But I think the point is clear. So I'll stop here. Thank you.
Thank you very much. A little note about the discussants. I've been kind to Roni because his formal discussant is going to be benign, I think. But there are some people in the panel here who are much less benign on this hypothesis. So there will be more coming. Judith, you're the mercy.
Yes, I am the nice one, and indeed, so I'm again in the sort of lucky position to talk about a presentation that I agree with. But let me ask you a few questions. I'll start. I have 4 questions, I think. I'll start from the more empirical one. So when you presented work that you conducted with Emmanuel Schemla and another collaborator, you showed sort of filler gap constructions, right? You showed us how ChatGPT-3 got much better than all the other models. So what does that tell us? So I'm wondering if you take it as like, well, it's just a quantitative thing. It just got better. Of course, it was trained on more. Who cares? Or do you think that if in the future we will have better models who can handle even your more sophisticated examples, then that would actually be something substantial?
Right, thank you. And that's a very important question. And I think in the case of GPT-3, things are a bit mysterious because like all the products of OpenAI, we don't really know what's happening there behind the scenes. But we do know that it's trained on a lot of data, and so many orders of magnitude above what children see. So I think the fact that there you start seeing an improvement actually suggests that these models, again with the caveat that we don't know what's actually happening with with GPT-3, but assuming that that the success is an LLM success there. Then it does suggest that with lots and lots of more data, these models can start approximating what children know. But children learn that or reach that knowledge after very few years of evidence. So in this sense, the relative success of GPT-3 serves to strengthen the argument from the poverty of the stimulus. These models can tell us when there is enough, when the signal is strong enough, and it just takes many thousands of years until we get to that point. And since children succeed with much less, they're somehow prepared. But of course, as with every attempt to draw a positive conclusion from these things, it has to be very tentative. Yeah.
And so related to that point, actually, so my second question would be, well, okay, so essentially, let's take this and also the I thought, very insightful and smart manipulation of you feeding sort of artificially too many of these filler gap constructions, like a lot more than would be representative of real input, then they can learn it. So let's take this as arguments or evidence for large language models being different kinds of learners than humans. So essentially, let's take them as not poverty of stimulus, but richness of the stimulus kind of learners. So they learn well from a lot of data. This is not what humans do. This is not what kids do. Fine. But they are this kind of learners. And so I think it's undeniable that they, as you said, they're efficient engineering tools. They can at least imitate or mimic language. What would that tell us about the mind or language or cognition? So assume that we agree, which some people don't, but let's agree that they are not like humans. But they do learn language in a certain sense, at least functionally. Would that be meaningful for cognitive science or linguistics?
So I'm not sure. So for cognitive science or linguistics, I would like to find a place where we find some organism or some other cognitive domain where what LLMs do is kind of the beginning of a good theory. If we find that, and it's possible that we'll find that, in which case this different kind of learning that these models exhibit can become very meaningful and can teach us potentially quite a bit. At this point, I'm not familiar with claims that, okay, so our linguistic cognition is completely different from LLMs, but this other thing that we do, or that this or that organism does, is a lot like LLMs. But that would be very interesting, and I'd be so again. I don't mean to be negative about LLMs. I think they're very impressive, and they could, in principle, be a good way to start understanding all kinds of other things, but I don't know what those other things are.
Okay, so I guess to rephrase this maybe, or push the parrot analogy a little bit, if we found other organisms that learned in this way, then they become interesting because they can explain something, right? So if humans evolved to learn language in one way, but maybe something else evolved to learn some communicative system in this way, then they're interesting, right? So, and then my final question is about the under the hood problem. So assume OpenAI just made it open source, was transparent about everything. If we understood exactly what was going on, so not just that they open it up, but we take the time and effort and energy to sort of track down all the parameters, the huge complexity, our best scientists will work on this for a long time, and we figure out exactly what's going on. Would then, so because I think your argument for LLMs not being a good scientific theory simply because they are black boxes, and so how could that be a scientific theory, is of course a really strong one, but one that is not an in principle problem, but more like a practical problem. So imagine OpenAI gives access to everybody, and we put a lot of energy into understanding it. Would then LLMs qualify as a theory, or at least a candidate theory?
Right. So that general methodological worry that I raised about starting from saying that the world cannot be understood, that worry will go away if LLMs become a way of saying the world can be understood, and if someone shows us how to read LLMs with all their hundreds of billions of parameters and all that, and if someone develops some clean mathematical theory that allows us to understand what is said there, then that methodological worry goes away, and it becomes more promising, because then we can start asking questions about, okay, so now that we understand what these models are saying, we can very easily go and check what they predict, and we can make progress in the usual way. So yes, indeed. Now, I think that the empirical failings that I went through with the typological, all the many different typological facts, and the inductive leaps that we make, property of the stimulus, and competence versus performance, and correctness versus likelihood. For all of that, we don't need to wait until someone comes up with that theory. There, we can already we can already use what we know from cognitive science to say, okay, whatever these LLMs are, they're not this, they're not us. Yeah, but for the rest, I would love to see a clean theory of how LLMs work, and which would allow us to, of course, to understand much better what's going on there. Yeah.
Thank you so much. Thanks, Ronnie, and thank you very much for the amazing talk.
Thank you.
Thank you, Judith. A few words about the organization. The way that the panels were set up and the days were set up was not based on the taste, scientific or whatever, of the organizers. It was on the availability of the speakers. So as it happens, the really ferocious LLM people are in the second week. And I hope that you'll be brave enough to reappear in the second week to face the thrashing, I should say. But so the closest that we have to that here, and poor Eva, she has had to carry, Eva Portelans had to carry the lance, which she wasn't really so much behind. So what I want to do is ask, first of all, yes, you get the first crack. But I also want to send a general message to the attendees in the wide spectrum. If you are standard bearers for LLMs and you want to brutalize Ronnie, please let me know, raise your hands and come in. There are some questions here which are sort of neutral, but I would really like to have questions that are as determined as the literature is when it says the Chomsky program is over and we've got another model. I want people that have feelings in that direction to express themselves here. But first, Eva, who does not feel that way. But go ahead.
No, I don't feel that strongly. Definitely not. I'm probably somewhere in the middle, but yeah, I guess there was a question about this in the Q&A, so I can kind of bring it up just to kind of clarify the sort of other perspective that to Ronnie's talk, which is that these models might actually be useful in some way to addressing these poverty of the stimulus type arguments. And the argument there is that these models could serve as sort of these proofs of concept of what is in practice possible versus what has been discussed in principle possible in terms of learning in the literature. And one thing I do want to stress, though, that and this is, I think, an important point is proof of concept type arguments they're not strong enough to be able to say specifically that we therefore have to dismantle all of our hypotheses about how humans learn or how humans represent language. Because all they can do is really just show what's in practice possible in models, and at most suggest that that may be also what is happening in people. And so they are sort of a weak form of evidence. So I don't think they necessarily, that's why I don't take the strong position that UG is not a thing. We are over with the sort of Chomsky tradition and program, but rather that this may be the beginnings of something that we now have these sort of other species of learners that are showing behaviors, at least that seem to mimic learning behaviors that we have possibly hypothesized could be learned or from different types of innate knowledge or biases. And so this is sort of just really what we are saying, I think, or a lot of us are saying on this other side, is just that, wait, maybe this is a time to reassess and think about, is there the possibility that we can actually find ways to use these models, interestingly, to try to readdress some of these debates. I'll stop there.
Good stuff. Thanks. Go ahead.
Yeah, so thank you. Yes, so I'm certainly not opposed to using these models to explore all kinds of possibilities and to examine proof of concepts in different ways. Did you have specific uses of this kind in mind, or because in general it sounds like a good thing to do? I'm certainly not against that. We do some of that in ourselves. The only question is where we use what you do with these models in these proof of concept cases, and what kinds of conclusions people want to draw from that. Yeah. So if you have concrete cases, I'm very happy to talk more about this.
Yeah, I think, this type of proof of concept evidence comes out of this whole literature around this Bertology setup, where we sort of probe these models, and not you, I think it may have been Charles this morning mentioned also the agreement data being sort of flawed in some ways, but that was one claim, that these models can learn things like subject-verb agreement and so on. And they've also been used to look at whether or not they can reproduce our grammaticality judgments for cases like gap construction and so on, again, with these types of benchmarks. And from that, not to say that those particular papers were trying to say anything about the learnability of these constructions, but I think what it's done is it's sort of opened a window towards, well, what are they doing exactly in the background? Are they actually learning these things? And if they are, can we use that as evidence that it's possible to learn these types of constructions just from corpora of text and transformer model architectures, which I'm not convinced is possible, I should say. I think there are personally flaws to transformer-based architectures, and as you've pointed out in your works with LSTMs and other types of architectures, like that they may not actually theoretically even be possible for them to learn certain types of hierarchical rule-based systems that we might actually have. So, but all to say that I am somewhere in the middle, saying that I don't want us to sort of completely block out the idea that this is actually a really interesting direction for future work, and that these models in some ways have allowed us to ask those questions and to start thinking about this new direction.
So
yeah, go ahead.
So my question is just what is it that we would be trying to show with these models? Because if it's just saying that it's possible to learn, that's something that we already knew. So there are old results showing that it's possible to learn much more complex things than anything that, I don't know, anything that I've had on these slides. For example, just from raw evidence. So we're going back to Ray Solomonoff, who I mentioned earlier. He a bit after his initial discoveries, he also gave us theoretical results on how we can learn just from raw input, and there are other results as well. So it's not that linguistics as a field believes that it's impossible to learn, and so therefore, if you show that you can learn, then you challenge linguistics. That's not the case. I think, I don't know, I haven't run the relevant polls, but I think most linguists would agree that we can learn a lot, and that's not how you reason about what we are. So the way one reasons about it is by coming up with a better hypothesis about, here's the programming language. So these LLMs are, as I mentioned, they are a UG. They are a programming language where the programs look different. They're configurations of weights, and so that's a hypothesis about UG. And is this new hypothesis about UG better than the previous one or previous ones? There were several. It's not that one would refute UG or the Chomskyan approach by showing that it's possible to learn. It's saying, well, we agree on the general game, the rules of the game of inference to the best explanation. Linguists propose these kinds of UGs, and we're proposing these new kinds of UGs, and ours are better. And that's a good kind of debate to have. Yeah.
Hey, Steve,
Oh, go ahead.
were you going to go? Sorry, were you going to answer, Eva? Go ahead.
No, I was going to ask a follow-up question to what Ronnie.
Do it.
Okay, yeah. So when you say that these models are UTs, is that meaning that, the assumptions that they encode are sort of where we begin? That is the UG. So they start with, general statistical based learning, co-occurrence tracking, and no other bias towards category learning or anything like that. And that's what you're saying. That would be their UG. That's their starting bias, and it's just a very, very close to blank slate. Is that correct?
Yes. Yeah, I don't know how close to a blank slate it really is, but yes, I mean, I think that's the hope behind these behind some of these claims, certainly, but I don't know. I think we don't understand enough about the biases of these models, but they are what they are. This is who we are, or that's the claim, and of course there are different architectures, and some claims would be, well, we don't know exactly what kind of architecture we are in this LLM world, but we're one of these, and it's essentially different from, say, a programming language for context-free grammars or something else, or Python, or
right, that are biased towards specifically learning, categories and rules that allow combinations of some kind. Yeah. Okay. Yeah. And I agree with that. I think maybe my point about learnability then is sort of a mischaracterization, where instead of sort of presenting this as two separate perspectives, it's really about seeing learnability as the scale, right? In terms of, this is what I'm getting from your perspective, is that innateness isn't necessarily one perspective, but rather sort of the question is more about what is there from the start. So that's the UG question. And how much of it can we sort of take away and learn is kind of the thing that this new LLM tradition is now, or body of research is now bringing, is that they're sort of saying we can take away more and more of that.
It might be. I'm not sure that that's what they're
doing,
because without engaging with what linguists have built for as part of the innate mechanism that we have, which are not about it's hard to learn this. It's about all kinds of things, like, for example, language after language shows this. So without engaging with that, it's very hard to tell what the LLM theory would be trying to use here in arguing that it's better, that the UG that it proposes is better.
Okay.
We can learn Yeah, most people would agree. Yeah.
That's getting to smaller niggles. So let's move to. I would like to move to something violent. Before Judith will not be violent. Before Judith picks it up, I want to ask Steve Hansen. I see you there. Are you prepared to play the angel's advocate? Steve, he would give you the ferocity that you want. Okay, go ahead, Judith, and we'll see you.
So I'm not going to be brutal, but maybe provocative. So let's, so here's a proposal. I just want to throw it out there to kind of merge the very computational perspective with the biological one. And so essentially from this discussion you had about sort of innateness or learnability being a continuum or more or less, here is one proposal. It may be the case that infants or children learn language in a very Chomskyan way, so through abstraction, generalization on the basis of very little data. And then once the critical period for acquiring a native language or several native languages closes, we become more statistical LLM-like learners, so essentially adults. So we know from a lot of work, empirical work in sort of artificial grammar learning paradigms, that for the same amount of data or the same type of data, artificial grammars, where there's variability, infants extract generalizations, whereas adults tend to, as much as they can, rote learn or kind of map the distributions and the statistics. So how about something provocative like we go from one to the other across our lifespan or something. So we have a biological window of opportunity when we have UG at full sort of, functioning fully and operative fully, then the parameters are set, or in whatever way we do this, the critical period closes, and that leaves sort of settings that leave a permanent mark or sort of shape our mind and brain in some critical way. Language learning remains, of course, possible throughout the lifespan, but will be qualitatively different. And so that qualitative shift may be a shift from UG type of parameter setting to a more cumulative LLM type of learning.
So I think that's a very interesting idea, and one would have to come up with a good story of the changes that happen, absolutely, and I think there might be very non-trivial changes that happen in how we learn things in general that correspond to that, and of course connect to your talk from yesterday. And yes, absolutely. I'd still be suspicious of any claim that what happens after the critical period is an LLM, for the simple reason that as adults we can do the A's and the B's and the C's and the D's from that example, and no language model at present can do that. So we probably change quite a bit during those years, but I don't think we change into anything that is similar to those LLMs. Yeah, though I don't know what we do change into. So yeah,
Gary, you're on.
Hi, sorry, I'll keep my camera off. I'm not in the best situation for Zooming right now, but I needed to channel some ferocity. I can imagine that it must be very frustrating to be a linguist in the generative tradition right now, and I guess one might say that this is what a paradigm shift feels like. So I'm squarely in the camp that this is sort of the final nail in the coffin of the UG program, although I really like your kind of framing of UG as this innate kind of programming language. The thing I would like to, I guess, challenge most is the very idea of a competence performance distinction as being this core foundational thing. To take one of your examples of a child walking, a child who can't walk does not know how to walk, has no competence for walking, right? We don't talk about acquiring walking. We talk about, the child learns to walk. Now, one could come up with a situation where, a person who is bound, tied up, an adult, right, can't walk physically because they're restrained, but they know how to walk, right? But just because one can create a situation like that does not make that distinction especially meaningful. And something that's been concerning to me for many years is that this distinction as a core kind of assumption of the generative program has led linguists in that tradition to collect very, very limited types of data, namely grammaticality judgments, right, from adults, mostly trained adults. Yet, a child, right, who can't make any of these grammaticality judgments, right, who would fail all of your tests that you are giving to LLMs, nevertheless has the ability, right, to speak whatever the underlying competence might be based on those results. So I feel like, given how much rests on this distinction, I don't know what we've gotten for it, right? But like it seems to create more baggage than solutions.
Ronnie, and that's not an LLM objection. That's just an experimental psychology, psycholinguistics objection. Go ahead.
Yes.
I'm sorry, can I jump in just to
Yes.
and babies? No. So there are two things that are just empirically not right. So there is classical work from Esther Tallon showing that actually babies who can't walk can walk or are able to walk. So we are born with a stepping reflex, and actually under certain circumstances, for example, if you put babies in water where they are supported by the water and they weigh less, then they continue showing the stepping reflex throughout. It never goes away. So actually the fact that they don't manifest walking because they are heavier than what their muscles can lift, etc., doesn't mean that they don't know how to walk. So this is actually factually not true.
But I would say, Esther Tallon would be the last person to say that babies have, a competence independent of performance. So walking to some extent is, a reflex, but actual successful walking is in mammals is not a reflex, right? We continually adapt to surface changes. There's a whole lot more. So a stepping reflex does not get you walking.
Yeah, so don't be tricked by the word reflex. Actually, there is evidence that even in newborns, there is cortical top-down modulation of the stepping reflex. So it's not that simple. So I fully agree. It's not a reflex, or it's not so simple as a reflex, but indeed it's not so simple even in babies. And then the other thing is just kids can give you grammaticality judgments. Just don't call it grammatical. You just say, this robot talks funny. Sometimes it gets it right, sometimes it gets it wrong. And then they tell you, oh no, now it got it right. Or now so you can
But the fact of the matter is that, when we tested with Anna and Kyle and a few others, so the grammaticality judgments of the GPT-4 compared to humans, GPT-4 outperforms humans, right? It's producing more normative grammaticality judgments. These are human adults, native English speakers. But we would not draw from that conclusion, right, that the adults are poorer at understanding or producing language, right? I think the fault is entirely in the kind of using grammaticality judgments as the entire basis for a research program. And then when people don't give the desired grammaticality responses according to existing theory, right, that gets ascribed to, oh, that's just a performance limitation. That's just because they can't hold it in memory. It's not, right? And that makes for a very weak research program. Its ability to actually deal with real data, no matter how elegant and beautiful the theories may be.
I don't understand in what sense. You've said quite a few things that I don't know if we have enough time for that, Stephen.
We don't, but it's going to go on in other sessions. Go ahead.
Okay, so do we get to come back to this in the panel discussion today?
Yes.
Or?
Yes.
Okay, so I'll let other people then.
But the thing is, where's Kyle? Why did he run away? You could have been given a harder time than you were given, but okay. Fine. There are other comments from benign people like Virginia and even who's on the other side, but seems to be merciful. Go ahead. Actually, Ava had her hand up first, and then Virginia, and then we're out of time.
Yeah, I was actually going to ask a question about kind of bringing both your talk and Charles's talk back to that example you gave about learning, the ABC or A to the N, B to the M, C to the N, D to the M language. And I thought it was kind of an interesting case because technically what ChatGPT said wasn't wrong. It was just a grammar that overgeneralized, produced strings that went beyond the specific set, right? So it was maybe satisfactory given the evidence that it had seen, but was over-explanatory and didn't just account for these specific strings that it did get to see. And so I wonder if really what's the question is it just that we haven't exposed these models yet to the right combination of experience and input that they are able to kind of get to the correct systems that we seem to think we have, rather than it's given its experience that seemed like the right explanatory sort of like hypothesis. So maybe is it that when we learn these grammatical systems, there's more to just how we learn language than the linguistic input we're getting, but we also get a lot of information from, how we create categories, how we sort of perceive the world that might change.
Okay,
the organizational systems
the
we choose.
question has been posed now. We have very little time left. Go ahead.
Okay, so we can, of course, talk much more about this maybe in the panel later on, but just quickly, I think we all have very clear intuitions about when a generalization is okay and when it's not okay. And there can be, of course, lots of borderline cases where we're not entirely sure, but given some data, some hypotheses are okay, and most hypotheses are terrible, even though infinitely many hypotheses are going to be compatible with the data, of course. And MDL is something that's designed to capture this sense that we have about when a hypothesis is good given the data. And of course, we can argue about whether that's exactly the right criterion or something else, and so on. But we have that intuition. It's quite clear that we all look at those data, and it can be children or adults, and it can be scientists or non-scientists, and we'd expect the same from aliens. We reach similar conclusions, and these LLMs just do something else. They fail to generalize, and when one looks at the learning criterion, it's quite clear why. It's not because they can't represent it. They're, as Ziegelman and Sontag showed a long time ago, in principle, you can engineer them to say anything computational. They're too incomplete. It's that they have the wrong learning criterion. They prefer the wrong things. They try to memorize the data. They overfit even when you try to fix it with regularization, and that's the problem. And therefore those failures are not an accident. It's not that it tried to generalize and it's kind of okay, but we don't. It really is not trying to generalize. It's trying to overfit, and it doesn't have a good way of punishing overly complex hypotheses.
Okay, no comebacks on that. Virginia, and then the last one is Gary raised his hand again, and then go and eat lunch.
My response is a response to Gary. So Esther Thalen's work showed that children do know how to walk before they walk by putting them in water and showing that it was a problem with their weight relative to the length of their legs and so on. And I think exactly the same thing can be shown with performance, so-called performance issues in language acquisition. That is, you can do things that will systematically alter the performance conditions. And if you show a difference in response as a result, you've got a good argument that it's limitations in the cognitive system rather than limitations in language that are causing the issue. And-
That's for Gary, and then Gary can answer, and then we'll cut it off. Go ahead.
Yeah. Learning to walk, learning to sit, these are really long, protracted processes with many developmental cascades. If it were, it takes many months just to learn to sit. As anyone who's observed real children can attest, there are average milestones, but the actual process for any child is a protracted process with enormous back and forth between the environment and the body, right? And I take the point that it's very instructive to examine, for example, what is the role of memory limitations, a particular kind of memory, one can get more specific, on certain behaviors. One can increase or lower memory load and so far. But that, interpreting that to mean that, oh, its performance makes assumptions about discrete modular systems that are, I would argue, in most cases, unjustified. And so it's not that, oh, if memory affects it, therefore it's not language. Memory is part of language. There is no language without memory, right? Now, as a cognitive scientist, we certainly want to know what is the role, what precise role is memory playing in a particular set of behaviors. But that if memory plays a role, it does not make it, right, not language. So that would be my response to that.
Okay, we can't hear you, Virginia.
We have a fundamental disagreement there. Maybe in the panel, we can go
Yes.
into this further.
We'll leave it with the panel, and I'll try a very dangerous experiment with the panel, and I may change my mind after 5 minutes, and you'll all agree. I'll try it open mic so that I don't have to mediate who talks, okay? But if it doesn't work, we go back to, okay, thank you, everybody. The next speaker will be
Thank you.
Thank you.
Carl Friston, who's in the background very quietly, and have a good lunch if it's that time of the day for you.